Good afternoon, guys. After I spoke with the 442s, all right, on Friday, I asked you guys to stick around just a little later so I can get a little bit of a Q&A session going on. It's probably better that I record this final lesson, our final 2-hour lesson, so that I can squeeze in as much content as possible and then still host my Friday for a 1-hour Q&A session to give you test preparation as well. All right. So for this class today, we're going to run through motor calculation, bring you back up to speed on those concepts. Run through a hermetic refrigerant motor compressor calculation, bring you back up to speed on that concept. Go through a welder calculation, bring you back up to speed for that. Been a little while since we've done one of those. And then once again, do a few more transformer calculations, at least one full one all the way through. On Friday, I will give you a breakdown of what's going to be on your final test, but that is also going to include voltage drop on that final test. All right. You're going to have the entire day to figure out that test, 24 hours as always, just to complete that assignment. But we'll do test review and things like that on Friday in our 1-hour class. Hey, so today I want to do this recording so that we can go through, we can do a few calculations together. You can watch this as many times as you want so that we're going over the same code rules. We're looking at the same multipliers, and hopefully it answers any questions that you might have about where we've been and where we're going to end up. Okay. I want to run through these, and it's very important that I do this in a recording because I won't have enough time to do all these calculations together in a 2-hour class after I answer all the questions and, everybody gets checked in and attendance done for Zoom. So I'm going to set this up on the YouTube page. All right. I'll upload this afternoon, and you'll have this time to review this class at your own convenience as many times as you like. All right, so we are going to be doing motor calculations, hermetic refrigerant motor calculations, welder calculations, transformer calculations, and I'm going to throw in a voltage drop calculation just so that you're up to speed for a bunch of the questions that are on your final test. All of these answers are available for you on Fanshawe Online. I'm going to pick and choose just some random ones for the sheets that you've been given, the handouts that were delivered to you, so that you can go through and you can follow along and double check the answers as I go through these questions. Sorry. So what I want to start off with is a motor calculation, and then I'm going to tell you to pause the video so that you can write down the information, and then I'll continue on with the calculation. All right. So first we're going to do a motor, then we're going to do a hermetic refrigerant motor compressor, then we'll do a welder, then we'll do a transformer, then we'll do voltage drop. All right. It's going to take us a little while to go through these calculations, but like I said, it's probably to your benefit, so you can watch this video as many times as you want, and you can follow along, pause, stop, and then whatever questions that you have about these calculations, please record them so that we can go through them and we can look at them on Friday in our 1-hour class. Okay. So right now, probably a good idea for you to grab a piece of paper and some sort of writing utensil. I'm going to come up with our first motor calculation, and we will start our evaluation from there, coming from section 28 in your code book. Okay, so what I've done is I have recorded one motor calculation from the advanced code sheets that are on Fanshawe Online. The answers are available to you for code sheet 3.7. And it's the center motor calculation for this one that I specifically have requested that we do. All right. This one specific motor has some restrictions to it. It's on a 600 volt system, 600 347 volt system. You are using TW75 conductors for this. Your termination temperatures, all of them are 75 degrees Celsius rated for all your termination temperatures. And for this one specific example, we are requesting that you install a bonding conductor, even though you're doing rigid metal conduit. All right. So you're going to need to size the disconnect. Your overcurrent device for this specific application is going to be a time delay fuse. We have to size our overload component. I want to take a look at that junction box and its distance, or the distance of the conductors feeding that motor. And your motor calculation is based on a 50 horsepower rating, 575 volts, 3-phase. Hey, your service factor 1.15. It is a varying duty motor with a 30-minute rating and a Class A installation. Okay, so installation on that motor is going to be at Class A. We're going to go through this entire calculation. So this would be a good time for you to hit pause and record all this information so that we can continue on with this calculation. Okay, so for this installation, we're looking at Advanced Code Motor Sheet 3.7. That's available for you on Fanshawe Online. You can see all these answers. We're just going to go through and figure out how we got there. 600 volts on that system. We're using TW75 conductors. Oh, look at that. 75 degrees Celsius termination ratings. And for this example, we're looking at installing a bonding conductor. Okay, this one specific motor, 50 horse, 575 volts, 3-phase, service factor 1.15, varying duty with a 30-minute rating with a Class A insulation. All right. When the sheet comes around, your standard sizes of disconnects are available for you. We're all good to go. Okay. Class A insulation on this one. Knowing that I'm installing 75 degrees Celsius rated conductors, I can't use the extension on the rule, right? I'm using 75 degrees Celsius rated conductors. I can't use the 90 degrees Celsius ampacity because I don't have 90 degrees Celsius rated conductors. So I'm looking at sizing my disconnect, my overcurrent being a time delay fuse, my overloads. I want to talk about that junction box for a second. We're doing rigid metal conduit, 50 horse, 600 volts. Okay. So because you guys are very close to writing your CFQs, keep this in the back of your mind. When you're looking at these two values, when you're looking at 50 horsepower and essentially a 600 volt motor, keep this value in the back of your mind. When you hit a higher voltage like this at 575 volts, you're about 1 amp per horsepower. So if you read table 44 incorrectly for this 3-phase 600 volt motor, and you come up with like a weird value of like 70 amps, I'd second guess that. Because you're about 1 amp per horsepower, right? So if you came up with a different value, like something like 52 amps, which you'll find from table 44, 52 amps, I would trust my gut on that one. I'd go with that value. Okay? You're 600 volts, you're 50 horsepower, you're about 1 amp per horsepower. So if you saw something like 60 or 70, that's a little high for me. I might second guess myself on that one and go back to table 44 and determine my full load ampacity for that one specific motor. So now that I've been given my full load ampacity for this motor, I can go through and I can start doing all of my calculations. Now, something to save some time on when you're looking at the CFQ and you're doing motor calculations on the CFQ, double check this service factor. When you go through the code, you're going to see that there's a variation between service factors, and it kind of comes down to like a trustworthy or an untrustworthy motor. If your service factor is less than 1.15 or not marked, you're going by a different multiplier than what you are for a service factor that's marked at 1.15. Okay, that's coming right from section 28. But at this point in time, we have a service factor of 1.15. So my multiplier for that service factor is based on sizing my overloads. But that service factor being a marked 1.15 coming from the code book gives you a different multiplier than 1.15. It's going to be 1.25 as a multiplier. So you are 1.15. So your multiplier for this motor is now going to be 1.25 times your full load current to determine your overloads. This is also the same multiplier for continuous duty service motors. However, this one is a varying duty 30-minute rating, so it's not going to be the same calculation. So pay attention to your service factor and what that value is, and the duty rating of your motor. If it's a continuous duty service motor, the same 1.25 is going to be your multiplier. So you only have to do this calculation once, but it's two different code rules. Calculation once, two code rules. Here it's a little different. We're looking at a varying duty 30-minute motor. Not going to be the same calculation. But observe that, and that might save you a little bit of time on your CFQ. So to size my overloads, I'm going by my service factor of 1.15. Okay? That gives me a multiplier coming from the code book of 1.25 of my full load current rating. At that point in time, my overloads should have a set rating of 65 amps. So that would be 1.25 times 52 amps as an FLA. My overload rating should be set for 65 amps. Okay, so my overload setting, 65 amps. 50 horse, 575 volt, 3-phase, service factor 1.15, varying duty 30-minute class A. Got it. Overload is going to be set at 65 amps. Conductors now. I'm going to need conductors to feed my motor. Okay. I have to observe my varying duty 30-minute rating. Because it's a varying duty, and it won't run for more than a 30-minute period, I come up with a different multiplier. And that multiplier is coming from a different table because it's not a continuous duty service motor. Okay? That multiplier is 150%, or a multiplier of 1.5. 150%. So I still am based on my full load current rating of my motor, but for my conductors, because of the demand on that motor, I'm at 150%, not 125, just because of the varying duty 30-minute rating. So I take my 1.5 and I multiply that by my FLA. So that's 1.5 times 52 amps, giving me a minimum wires ampacity of 78 amps. Three-phase motor, take that value, go to table 2. At that point in time, I'm installing a number 4, good for 85 amps. Fair enough? Fair enough. Okay. Going back to that NEMA chart that you have. Like my coach loves that one. Based on your 50 horsepower, your 575 volts, that would be a NEMA 3 size for that specific installation. Okay, so we've checked off service factor, varying duty, 30-minute rating. Class A, wow, that takes into consideration up here. 75 degrees Celsius termination ratings, you're using TW 75 degrees Celsius conductors. 50 horse, 575, 3-phase, 52 amps as your full load current rating. So your conductors are going to be number 4. Good for 85 amps. All right. Now, the next portion in the equation, we can't necessarily do bonding conductor just yet, so we'll hold off on the bonding conductor. In this specific sheet, even though you're running rigid metal conduit, we're requiring a bonding conductor. All right. The next one, kind of running through this whole dimension here, time delay fuse, looking at my overcurrent protection. Once again, overcurrents are protecting the motor. Overloads are protecting your conductors. These overloads will open at 65 amps, which is 125% the FLA. Because of our varying duty service motor, we have a multiplier of 150%. So my conductors are sized larger than my overloads. Overloads will protect my wires. Now for a time delay fuse, my multiplier becomes 175%, or 1.75 as a multiplier to figure out what size of overcurrent device I'm going to install for this 52 amp, 50 horse, 575 volt three-phase motor. 1.75 becomes my multiplier. Multiply that by my FLA, giving me 175, 1.75 times 52. At that point in time, you should come up to about 91 amps. 91 amps for that installation. All right? But the problem is they don't make a 91 amp fuse. You can't go to the wholesaler. You can't go, to Electrozad or, Ruddy or whatever and say, hey, I need a 91 amp fuse. They don't make a 91 amp fuse. The problem is that I can't exceed that number. That's my maximum calculated overcurrent device. If that landed on a square 90, we'd be in good shape. I could buy a 90 amp fuse, but I can't exceed that 91 amps. So I can't go to a 95 or 100 or 110. I have to go lower than that 91. At that point in time, I would absolutely need to install a 90 amp time delay overcurrent device to install inside this disconnect. So calculated value is 91. My installed value, 90. This 90 amp fuse basically determines my disconnect size. And on this sheet, you're going to see standard sizes of disconnects. At that point in time, a 90 amp fuse is not going to fit in a 30 or a 60 amp disconnect. 90 amp fuses will absolutely fit in a 100 amp disconnect. So I would install a 100 amp disconnect for this one specific motor calculation. I'll give you a second just to record these values. And by now, I'm sure you are fully capable of doing a conduit fill calculation. So please admire the fact that we're going to have to size a bonding conductor and you are using rigid metal conduit. When you look at your overcurrent device being 90 amps, I can now size my bonding conductor correctly. Okay, at that point in time, I believe for my bond, coming from table 16, it's going to be a number 8. For 90 amp overcurrent device, not exceeding 100 amps, number 8, copper. Same as the rest of your termination points, same as the rest of the chemical composition of your conductors. So you're going to end up with a number 8 coming from table 16. I am fully confident in your abilities to do a conduit fill calculation for rigid metal, incorporating a number 8 bonding conductor, which means you need a red, a black, and a blue current carrying conductors at number 4 TW75 insulation ratings, plus a number 8 at TW75 insulation ratings. And I believe if you go through and you do the calculation correctly, you should end up at a 27 millimeter rigid metal conduit. Okay. The reason why I can't use the 90 degrees Celsius ampacity for that Class A motor is that all of my termination temperatures are based on 75 degrees Celsius, and so is my conductor. So I cannot use the 90% rule for that calculation because I'm not running T90s. I'm not running RW90 XLPE. I'm running TW75. I can't get away with that calculation. Okay, I can't get away with that 90 degrees Celsius ampacity because I'm not using 90 degrees Celsius wire. All right? So just take a second and record that information. This will be a good time for you to hit pause, go over those calculations if anything is confusing. If you have a question, record it, write it down. We'll talk about it on Friday. Okay, so make sure that you have those values recorded, because there's an important rule that I want to accentuate before I let you go on motors. Okay, this very important rule is kind of understated and it's not really observed to its full ability. All right, 28104 subrule 3. Pay attention to this one. Okay, this one got me on the CAQ, and I'm pretty sure I got this question wrong on my CAQ. All right, a very long time ago. Question 3 specifically, or sorry, 28104 subrule 3 says where table 37 requires insulation temperature ratings in excess of 75 degrees Celsius, the motor supply insulated conductors shall A, be not less than 1.2 meters long and terminate in a location not less than 600 millimeters from any part of the motor or motors rated less than 100 horsepower. And then part 2 to that rule says 1.2 meters from any part of the motor for motors rated 100 horsepower or larger. So it's all the interpretation of the rule and how you have to understand this one. First of all, they're looking at temperature ratings in excess of 75 degrees Celsius. Well, for this specific motor, we are 75 degrees Celsius rated conductors. And we are using a Class A motor, whether it's totally enclosed, non-ventilated, or anything else, open drip proof, doesn't matter. Okay, so for this specific motor, this rule doesn't necessarily apply because this motor isn't going to exceed 75 degrees Celsius. Okay, we're not running 90 degrees Celsius conductors. We don't necessarily need to follow this exact rule when we are looking at this connection from junction box to motor. However, when it changes to something else, to anything other than 75 degree Celsius rated motors for your conductors as well, and you have to increase your insulation rating on your conductors, now this value applies. And it's one of those rare circumstances in the code book where it tells you how long your conductors have to be. So if it's above 75 degrees Celsius for that insulation rating of that motor, your conductors have to be 1.2 meters long. And then they have to be a certain distance away from the motor based on the horsepower rating. So from that junction box going to that motor, those conductors are going to be 1.2 meters long. Now that determines where your junction box is going to be in relativity to your motor. And those conductors have to be 1.2 meters. Okay? Depending upon the horsepower rating of the motor, if you are under 100 horse, so not 100 horse, you have to be under 100 horse, which is our situation right now. We're at 50 horsepower. Those conductors have to be 1.2 meters long, but this junction box can't be any closer than 600 millimeters. That physical distance, not the length of the wire, that physical distance between junction box and your actual connection to the motor can't be less than 600 millimeters. If this one specific motor, as a hypothetical, was 101 horsepower, 101 horsepower, this junction box, therefore, this connection point compared to this connection point has to be 1.2 meters away, which by default means that your conductors are going to be larger than 1.2 meters. Just by default. That's going to be measured in a straight line from this point to that point, 1.2 meters, which means your conductors will obviously be longer than 1.2 meters. Okay? The idea behind that is 100 horsepower or larger motors are going to dissipate more heat. Okay? They're doing heavier loads, heavier lifting, running heavier conveyor belts, whatever the case is, they need to dissipate more heat. We don't want our conductors as absolutely close as possible to that motor when they are dissipating that heat or they're running full tilt. Okay, so be very careful with this on your CAQ. I bring that up in every one of my advanced classes because I'm pretty sure I got that question wrong, because I'm pretty sure my question on the CFQ for my motor calculation was a 75 degrees Celsius conductor. And it was a 75 degrees Celsius motor here. And I'm pretty sure I answered that question wrong when they asked me how far does that junction box or that connection point need to be away from the motor. I'm pretty sure I answered that wrong. So I always bring this one up in advanced code. Pretty sure I got that one wrong on my CFQ. Learn from my example, pay attention to the question and the wording of the question. Okay, number 8 bond coming from table 16. Good to go for that calculation. 27 millimeter for my rigid metal. Okay, that's the interconnection. Going to my motor, 100 amp disconnect, number 8 bond, 90 amp fuse. Keep in mind there are separate code rules for determining if that fuse will not permit the motor to start on startup. You may need to increase that, or you may need to do due diligence and reduce the load so that motor isn't starting under full load all the time and your overcurrent devices keep opening. Okay, be very careful of that question. Okay. The next example that we're going to run through is a hermetic refrigerant motor compressor. So grab a new sheet of paper, get something ready to go. I'm going to come up with another value for a hermetic refrigerant motor compressor so that we're ready to go for one of those calculations. All right, welcome back, guys. We're now going to do a hermetic refrigerant motor compressor calculation. All right, and if you pull up your examples that you have on Fanshawe Online, we're going back to a 3-phase calculation coming from sheet number 1, hermetic refrigerant motor compressors, and we are doing number 3 on that sheet. We're looking at 3-phase hermetic refrigerant motor compressors. Now, another little memory egg thing here, little aid, all right? Be very careful when you're looking at these values, specifically 3-phase, okay? It could be single phase. Be very careful with that. That's the difference between table 44 and table 45. Big difference, okay? In this example, we are looking at this hermetic refrigerant motor compressor from sheet number 1, calculation number 3, 208 volt 3-phase TW75. In this case, we are required to install a bonding conductor. We're looking at EMT as a raceway. And we're 75 degrees Celsius termination temperatures on everything. Okay? So take a second. You can record these values. And then I kind of plainly wrote this out over here for minimum and maximum ampacities of your overcurrent device. Maximum being 65%, the locked rotor current, and 50% of the locked rotor current for your installed minimum fuse size. Okay. Also across the board, you're at 140% for your overload calculation. Okay, so record these values. Take a second, new sheet, look at those. Maybe make a note, jot that down for your overloads, overcurrent component, 30 horsepower, 208 volt, 3-phase, and I want to look at my rated load current and my locked rotor current. Okay, beginning steps. I have to figure out what my rated load current is, my RLA. Very similar to a normal motor calculation. I have to observe 30 horsepower, 208 volts, 3-phase. Once again, be very careful of the 3-phase or single-phase thing. Okay. At that point in time, you can take that 30 horse, 208 volt, 3-phase, go to table 44, and come up with your rated load current of 88 amps. That's your rated load current. Okay. Coming directly from section 28, the difference between your rated load current and your locked rotor current is a multiplier of 6. So step number 2 would be to look at your locked rotor current and calculate that based on your rated load current. So you are at that point in time 528 amps locked rotor current. I need to know that locked rotor current for when I'm calculating my overcurrent devices, which therefore reflects my disconnect size, which also might reflect my conductor size, which would reflect my raceway size. Okay, so we can kind of go anywhere now that we have those two numbers. We have locked rotor current and we have our rated load current. I don't know, I got these values on here. I might as well start with overloads. Okay, your overloads are based on your rated load current at 140%. So you are 1.4 times 88 amps as your rated load current, which means your overloads are going to be set at 123.2 amps for your overload setting. 1.4 multiplier at your rated load current of 88 amps, giving you 123.2 amps rating or setting of your overload component. That's your overload relay. We can go now to conductor gauge. Okay, 75 degrees Celsius conductors, 75 degrees Celsius terminations. I'm looking at 125% my rated load current. So I am 1.25 times 88, giving me a minimum conductor ampacity of 110 amps. Okay, that point in time, 110 amps required load, 75 degrees Celsius termination temperatures. I have to go down to a number 2 conductor, good for 115 amps. I am required to install a bonding conductor. So I do have to look at the conductors that I install being number 2s, TW75, good for 115 amps. And I can size a bonding conductor. But I got to know my overcurrent protection first, or I have to look at the maximum capabilities of my conductor. Overcurrent protection as a maximum is going to be 65% of my locked rotor current, or as a minimum, going to be 50% of my locked rotor current. My locked rotor current is a different calculation than my rated load current. So now I'm interested in this number, that 528. Sizing overcurrent devices as a minimum or a regular installed overcurrent device, I'm looking at 50% of my rated load current. So that would give me 0.5 times 528, 528 amps. Half of that, I'm looking at 264 calculated amps for that. Obviously, I cannot exceed that 264. They don't make a 264 amp fuse, so I now drop down to my minimum installed or my regularly installed fuse of a 250. 250 amps. Nominally installed fuse size. Can't exceed the 264, 250. That's my installed value for my regular fuse size. However, I can increase that if the motor isn't permitted to start. The hermetic refrigerant motor compressor isn't permitted to start. I can go to a maximum fuse size at that point in time. And that's why I had it written over here. My max fuse I can go with my same rated load current of 528 amps at a 65% multiplier. My max fuse at that point in time will be calculated at 343.2 amps. Maximum fuse capability at 65%, the rated load current of 528 amps. Once again, I can't exceed that number. So I go back to table 13 and I find out that a 300 amp fuse will suffice. So I can increase from a 250 to a 300 if that rated load current is too high for that hermetic refrigerant motor compressor to start. So a 250 or a 300 amp fuse, doing the installation of number 2 conductors, going to table 16 for your bonding. At no point in time does it ever have to be bigger than a number 2. But looking at my overcurrent capacities, I can install a number 4. A number 4 bond for that. Just like the previous calculation, I'm fully confident in your abilities to do a conduit fill calculation. At that point in time, you should be a 35 millimeter EMT. Okay? Now, regardless if you install your minimum or your maximum fuse size, we can still size that disconnect. Because they only come in nominal sizes, the disconnects. So if you install a 250, we need a certain size disconnect. If you install a 300, we need that same size disconnect. Okay? At that point in time, you're either going to put in a 300 amp fuse or a 250 amp fuse max reg. What size does that disconnect have to be to accommodate a maximum 300 amp fuse or a regular or minimum installed fuse size, 250 amps? It's going to drop down to be a 400 amp disconnect because they are nominal sizes. That 400 amp disconnect will suffice the 300 amp fuse. If that's the worst case scenario, it'll also hold the 250. Okay. Once again, questions or concerns on that, please record them. Please record your questions and concerns, and I have all the time in the world for you on Friday to answer all your questions. Record these values. Now would be a good time to hit pause so that you can go over those calculations, double check with yours to mine, and then we're going into welders. We're going to do a welder calculation after this. Okay, I'll put the next one on the board and we're ready to go. Record these values, hit pause. I'll have a new circuit for you on the board in just a second. Okay, welder calculation, advanced code, welders. This is coming from the heading 3-phase welders 2008 master with feeders. All right, and we're looking at the second one on that sheet. All right, the second one on that sheet is a 3-phase welder, 208 volts, 15 kilovolt amps with a 90% duty. Okay, 3-phase values. We first need to figure out what our rated primary current is going to be. Okay. This installation is going to be in rigid steel, and we're going to size the minimum ampacity for a receptacle as well as an overcurrent device and the disconnect. Okay, so take a second. You can record those values. You can find these answers on Fanshawe Online. We'll go through this calculation in just a second. This would be a good time for you to hit pause and record these values. Okay, glad you got those written down. Let's get going through this calculation for a three-phase welder. All right, three-phase, 208, 15 kVA, 90% duty rating on that welder. Means we're going to come up with a different multiplier. All right, so first thing we have to do is calculate our rated primary current. Rated primary current is an Ohm's law calculation. You are looking at 15 kVA, or at this point in time now VA. Divide that by our nominal 208 volts times the square root of 3, giving us a rated primary current, an RPA, 41.636 amps. 41.636 amps. Good. Simple Ohm's law calculation. 41.636 amps as a rated primary current. Good. Calculated that one. Now that we have our RPA, our rated primary current, we can go anywhere through this calculation. We can keep going all day long. All right? Rigid steel, yeah, we got to figure out conductor size. Now we're going to wire for that. Right? To figure out what our multiplier is, to determine our conductor's ampacity, we have to observe this 90% duty rating on that specific welder. Go back to that respective section, and your multiplier should turn out to be 0.95 as a multiplier for determining conductor's ampacity. So I would take my rated primary current of 41.636 amps and multiply that by 0.95 because of the duty service cycle on my welder being 90%. That's where I generate that 0.95 from a certain section in the code. That comes down to a minimum conductor ampacity of 39.554 amps. Three-phase calculation, take that number for 75 degrees Celsius conductors, 75 degrees Celsius termination ratings. Not concerned about a bonding conductor in these specific calculations. Take that 39.554 to table 2, and I believe you are installing a number 8 conductor at that point in time, capable of handling a maximum of 50 amps. Important number for us. 50 amps is the maximum capability of that conductor that I have chosen for this three-phase 208 volt, 15 kilovolt amp, 90% duty cycle welder. My rated primary current is 41.636 amps, and I've selected a number 8 conductor, good for 50 amps. This number and this number now can come into consideration when I'm sizing my overcurrent capacity. Overcurrent capacity is based on two things. Number 8 TW75 50 amp conductors. Number 8, TW75, 50 amp conductors, or my rated primary current, 41.636. First calculation, you are looking at 200% of your rated primary current to determine your overcurrent device. So you are 2 times 41.636 amps, giving you a calculated value of 83.272 amps, or 200% the capacity of your conductor, in which you chose number 8, TW75. So I am 2 times 50 amps availability on my conductor, giving me 100 amp overcurrent device. I can therefore compare the two, and I can choose the lower of the two. At that point in time, I'm going to look at my 83.272 amps as being the lower of the two of my calculations. Now, I'm not permitted to exceed that 83.272, so I don't necessarily need to worry about this calculation, the second of my two, calculating up to 100 amps. I don't necessarily have to worry about this one. 83.272 is going to be the ampacity that I'm going to run with. However, I'm not permitted to exceed that value. So at that point in time, I would take that 83.272, go to table 13 and figure out what nominal fuse size I would install. And at that point in time, it's going to be an 80 amp overcurrent device. Okay. If I'm going to install an 80 amp overcurrent device, that's not going to fit in a 60 amp disconnect. I therefore need a disconnect to be 100 amp three phase to accommodate this 80 amp overcurrent device. Now, the ampacity of my receptacle has to suffice the rated primary current of my welder. And since they don't make a 41.636 amp receptacle, I now kind of have to bump up to the next nominal size. Now, I'm not going to give you a configuration because configurations for welded receptacles are not in the Canadian Electrical Code book. You would order this from your manufacturer knowing your rated primary current. And at that point in time, the minimum ampacity of that receptacle for this respective welder would be a 50 amp. Okay? If they made a 40, that's no good because you're 41.6. You've exceeded the rated primary current of your welder. So you're going to have to put in a 50 amp, just a nominal size. Okay? It's going to be three-phase, 208 volt, 50 amp rated. So the 50 amp receptacle would be the one that you would install. Based on the welder, you may have different configurations. It's not in the code book. You just know that your receptacle has to be good for 50 amps because you've done the calculation. When you go through and do this calculation, you also figure out that you're running number 8 TW75 conductors with a ampacity of 50 amps. That 50 amps matches the receptacle, which exceeds the rated primary current of that specific welder. Your overcurrent device being installed is going to be an 80 amp overcurrent device to be installed in a 100 amp disconnect. So we're in good shape. We've done this calculation correctly. In this specific sheet, we're not required to install a bonding conductor. So once again, I am fully, trust your capabilities of doing a conduit fill calculation, once again, for rigid steel. At that point in time, when you look at these calculations for your rigid steel installation, 3 number 8s, you're going to be a 21 millimeter rigid steel. 21 millimeter rigid steel. Okay. Now would be a good time. Oh, there's a glare on that. That's number 8 over here. I'm sorry, there's a glare there. That's number 8 TW75. That's your installed conductor ampacity and gauge. Okay. So take a second. You could probably hit pause right about now so you can look at these values, double check your calculations with my own. Once again, these answers are available for you on Fanshawe Online. Double check these calculations, hit pause, take a look at this. I'll be back in just a second and we'll talk about transformer calculations and then do one voltage drop calculation from front to back, and then we should be in good shape. Okay? Take a second, go through, look at those calculations, double check your welder information, make sure you're on point. Okay, almost there, guys. Advanced code, transformers, 3-phase transformer calculation this time. This is coming from sheet number 2 and the second transformer on sheet number 2. Okay, your speculation or your specifications for all these components are 75 degrees Celsius rated. That's conductors, that's transformer, that's termination temperature, everything's 75 degrees Celsius. 3-phase transformer, 600 12208, dry type. Kilovolt amp rating is 112.5, primary and secondary. So we'll be looking at a 600 volt primary and a 208 volt secondary. If we're looking at current calculations, determining my available primary current and my available secondary current and how those values pertain to the code. This would determine the ampacity of the panel that you could install on the secondary side of the transformer, being 12208 3-phase, dry type for these specific transformers. Okay, so now would be a good time to hit pause, pull out a new sheet, record all of this information, put this down so we can start doing the calculation in just a few seconds here. Now would be a good time to hit pause, record all this information so we can begin with our calculation. Okay, transformer sheet number 2. Okay, all these answers, once again, available for you on Fanshawe Online. We're going to size the disconnect. We're going to size the overcurrent device. We're going to size primary current, secondary current, and observe the code rules of what we're talking about for wire ampacity and overcurrent protection. Now, we do typically put the overcurrent device in the primary circuit. That protects the transformer. However, it's not uncommon to have secondary fuses before it hits the panel over here. That's not an uncommon thing. That might be a specification of your respective location or where you work, right? So how I've drawn this, these are break lines to show the difference between this portion of the diagram and that portion of the diagram. In real life, this break line would meet that break line. That goes back to intermediate prints, basic prints when we talked about that. I'm just giving you a bit of a separation so that I've got some room to write some of these calculations down. Okay, so first things first, we'll look at current values. We'll look at our current values. And I really wanted to go through this again because I am sincerely sorry, and I really do apologize for my previous video about transformers where my audio was not so good. I'm really hoping that this is much better, and I'm doing this in a different manner using just my laptop, not my external camera. Okay, so I really do want to apologize for that. Believe me, I'm going to make it this easy for you. All right. This is why I wanted to record this. So I am looking at 112.5 kVA on this specific transformer. That value is going to equal my primary current and my secondary current when I observe the fact that I'm looking for a 3-phase current value, primary and secondary, via transformer action. Now you should be far enough along in Theory A with Mr. Mankulich so you can determine primary current versus secondary current for a 3-phase transformer. Calculating primary current, I'll be looking at my 112.5 kVA. So I am 112,500 VA on my primary and my secondary side. Now, a theoretical perfect transformer has no losses. Once again, transformers are our most efficient machines that we know of in our trade. Okay, so I'm looking at 112.5 kVA or 112,500 VA, primary and secondary. Power in equals power out. Theoretically perfect transformers. Okay, take that value, three-phase transformers, divide that by my 600 volts primary times the value of square root 3. And if you do that calculation, you should come out to a primary full load current of 108.253 amps primary. Oops. FLA. A primary full load current value of 108.253 amps primary current. Okay? Once again, power in equals power out. We can do almost exactly the same calculation to determine my secondary current. At that point in time, primary current equals secondary current, primary kVA equals secondary kVA. I had the same 112,500 VA, 208 volts multiplied by the fact of square root 3 or 1.73, whatever values you choose to use. And at that point in time, you should come up to 312.269. Secondary FLA of that given transformer. Okay? So that's also neglecting hysteresis, eddy currents, heat losses, vibrational losses, things like that. We're looking at this transformer being theoretically perfect. All right, now that may change for your Theory 8 course. For code, we're going to keep this nice and simple. Primary current value going to be 108.253. 108.253 amps primary. And on the secondary side, I'm looking at 312.269 amps on my secondary side. Okay? Those are my primary full load currents and my secondary full load currents. All right? When we're looking at this specific transformer, we can now start wherever we want. Okay? Majority of the time, like I had stated, your overcurrent device is going to be on the primary side of the transformer. This is primary side over here. This is our 600 volt side on that side. All right? So I am concerned with my 108.253 amps. I am concerned with that value for right now. Okay? To size my ampacity of my conductors to go from my disconnect to my overcurrent, from my overcurrent to the primary side of my transformer, I have a simple multiplier. And that simple multiplier is going to be 125%. 1.25 times my primary FLA. At that point in time, I am 1.25 times 108.253 amps, giving me a calculated value, non-continuous for my conductors, being 135.316 amps. 135.316 amps for my conductors. That also directly reflects my fuse, my overcurrent protection, specifically for this transformer. Okay? Now, it's a little different from there's two hermetic refrigerant motor compressors and a little different from motors as well. If I calculate 135.316, that's a non-continuous load, which means I'm already protecting my transformer with my conductors. So I'm going to size my conductors capable of handling the 135.316 amps. And at that point in time, I take that value to table 2 and I see that my 1-aughts are going to suffice for that installation. 1-aught conductors are going to be good for that. 1-aught conductors are capable of handling 150 amps. TW75. Everything 75 degrees Celsius rated. So I can now look at that 125 amp multiplier based on my 108.253 amp primary rated current. Know that I'm expected to see no more than 108, but that's going to be a continuous load, so I now have to size my conductors based on 125% the available ampacity on the primary side, and I end up putting in 1-aughts good for 150 amps when I calculate 135.316. Now, like I said, this differentiates a little bit between transformers versus motors, hermetic refrigerant motor compressors, and welders. I'm installing the 1-aught conductors that are good for 150 amps, but I wouldn't want to downsize my current value. I don't want to choke that transformer in this situation. So at that point in time, the same multiplier exists, being 125% my primary FLA, for sizing my overcurrent device. My overcurrent device at that point in time is the same multiplier at 125%, being 135.316 amps. Take that value and the conductor gauge that you have selected to table 13, once again. And if I take those values to table 13, they do make a 150 amp fuse, and I am allowed to exceed that 135.316. I'm within range on that one. So I can install a 150 amp fuse. Totally. For that one specific calculation. Okay? So I know that I'm putting in a 150 amp fuse. My conductors are good for 150 amps. I suffice my primary current of being 108, and I'm not worried about choking down that transformer yet. If something were to go wrong, my 150 amp fuse will catch that, and my 1-aught conductors will suffice. They'll handle the load. Okay? To accommodate 150 amp fuses and my conductors rated for 150 amps as well, my disconnect size at that point in time would have to be a 200 amp disconnect to accommodate the 150 amp fuses. Primary side, these are all my calculations so far. Now I know that I'm putting in 1-aught. That's good for 150 amps. I'm installing 150 amp fuses. I've calculated my primary full load current rating. I'm putting in a 200 amp disconnect on my 600 volt side. Once again, I fully trust your abilities to do a conduit fill calculation. Also incorporating the bonding conductor that we need for this installation, being a number 6. Coming from table 16. Okay. The minimum size EMT that you're required for that installation, once again, coming from the sheets that are available for you on Fanshawe Online, transformer sheet number 2, calc number 2. Okay. Your EMT size is going to be a 41 millimeter. That accommodates your 3 1-aughts, line 1, line 2, line 3, primary at 600 volts, number 6 bond all the way through in an EMT raceway, 41 millimeter. Take a second and absorb that information for the primary side of this transformer calculation. And in just a second, I'll come back and I'll do the secondary side when we're looking at the X side of the transformer, X1, X2, X3, line 1, line 2, line 3, red, black, blue, secondary side of the transformer. Because now we're dealing with multiple voltages. And if I have a 120, 208 volt system on the secondary side, I'm more than likely going to be in a Y connection. Okay, so absorb that information for the primary side. In 2 seconds, we'll come back. I'll have a blank screen and we'll do the secondary side. Okay, secondary side, transformer calculations. We're looking at 312.268 amps on that 112.5 kVA transformer with a secondary output voltage connected in a Y configuration of 122.08. So my full load current rating on my secondary is 312.269 amps. To figure out my conductor's ampacity on this side, the secondary side of my transformer, it's the same calculation as the primary side. I'm going to take my 312.269 amps, and I'm going to multiply that by 1.25 as a multiplier, or 125% the full load current rating of the secondary to determine my conductor's ampacity. If I do that calculation, 312.268 amps multiplied by 1.25, I end up coming up to a value of 390.336 amps, non-continuous on the secondary side of my transformer. Now, like I said, it's not uncommon to have a fuse on this side. In this case, it's not necessary, but watch for that on the CAQ. Okay? Watch for that on the CAQ. 390.336 amps on the secondary side for this specific transformer, rated at 112.5 kVA, 122.08 volt output. To determine my conductor's ampacity, I now take this 390.336 and I go to table 2. And if I take that number to table 2, I should find that I'm going to install a 600 kc mil conductor, good for 420 amps per conductor. 420 amps per conductor. Okay? Because my ampacity changes from primary to secondary, keeping my same value of 112.5 kVA, I now have to observe this value and size a bonding conductor on the secondary side of my panel now, of my transformer, going to my panel. I now have to size a different size bonding conductor for that. At no point in time would that bonding conductor ever have to exceed 600 kc mil. On the primary side, on my 600 volt side, we had a number 6. On my secondary side, for your bonding conductor, once again, table 16, I am therefore installing a number 2 bonding conductor on my secondary side. Because of my 450 amp value, or the calculated 390.336 amps at 125%, my secondary's rated current, full load current rating on the secondary being 312.269. I'm going to end up at a number 2, TW75. Everything. 75 degrees Celsius terminations across the board. Now, once again, I've said it probably 7 times today. I'm fully confident in your abilities to do a conduit fill calculation. However, just to speed things along, if you look at your 3 600 kc mil conductors going into one raceway accommodating a number 2 TW75 bonding conductor, you would need a 91 millimeter EMT. A 91 millimeter EMT. Trade terminology, 3.5 inch. 3.5 inch you would need to suffice that panel. Okay. Now, looking at that available ampacity and what that transformer would put out, okay, this is not going to be on your test. However, this would be valuable information for you in the future. You can label that panel as having a maximum ampacity of 390.336 amps based on the maximum ampacity of your conductors, based on this fuse feeding that transformer, protecting the entire circuit. This panel would be a therefore 400 amp panel. That's not on your final test. for code anyways. That might be on for prints, but not for you 442s, okay? At that point in time, your conductors are good for 420 amps at 600 kc mil, 3-phase, 12208 on this dry type transformer. That's where we're generating that 1.25 from. Okay, that would be a 400 amp panel to suffice the load for whatever you're connecting, non-continuous at 390.336 amps. Okay, that's your calculation for a transformer. All right, 200 amp disconnect, 600 volt side, 150 amp fuses primary. All right, 600 volt system, delta connected primary to the transformer, drop down, achieve your two different voltages, your 12208, probably going to be the most common, whether you're 309A or 442, 12208 volt stuff. There is a possibility for a 460 operation too, but that's okay. It all depends on your secondary voltage and what you're looking for. All right. So these are transformer calculations. We have one more to run through. I understand that we're at, an hour, 10 minutes here. I'm going to do one voltage drop calculation going in one direction and then in the reverse direction. That'll be it for the afternoon. All right. So once again, we'll do a voltage drop calculation. I'm just going to create something right here. All right. And we'll go through a voltage drop calculation together. Then I release you for the evening. Once again, record all your questions. If you have anything about this calculation, ask me on Friday. Okay. Welcome back, guys. We're going to do a voltage drop calculation. All right, maybe the more common way of doing a voltage drop calculation, more so knowing your distance rather than your allowable distance, you can run a specific gauge of conductor. You do not need to memorize these calculations. These values are apparent for you, okay, in Appendix D in your code book where we're about to go to. All right, given in this equation, we're looking at a voltage drop calculation for a 120 volt circuit. Okay, 2-wire circuit, 120 volt, all right? At this point in time, we're not going to exceed any more than 3% voltage drop. Okay, that's the speculation, okay? That's the given information for you in this one specific question, all right? 3% voltage drop. This may change on an upcoming evaluation, right? Whether you maybe have a maintenance person available to observe these circuits 24/7, 365. Okay, this may change. I'm giving you some information to your upcoming evaluation. 3% might change a little bit, maybe. Okay, voltage drop, 120 volts, 3%. I'm looking at 12 amps non-continuous. Okay, taking the guesswork out of the calculation. I'm not expected to see any more than 12 amps. However, my load that's 12 amps is 90 meters away. And I am running 90 degrees Celsius rated conductors, and they are constructed of the chemical composition that we recognize as copper. Okay, 12 amps non-continuous load, 90 meters away, using 90 degrees Celsius copper conductors, 120 volt circuit, 3% voltage drop, maximum, no more. Okay, 12 amp load, because I don't know what it is, it's non-continuous, I am subject to Rule 14104. Does that make a difference for us right now? No, not really. Because I know that I'm not going to be able to go 90 meters on a 12 amp load with 14 gauge conductors constructed of copper with 90 degrees Celsius insulation. I know I'm not going to be able to go that far. Especially 90 meters. That's a football field. Right? That's a long way away. 12 amps load, 120 volts. Long way to go. Okay? So, if I taught you basic and I taught you intermediate, I would have told you the KISS method. KISS method is this. Remember this. Distance. For us, 90 meters. Divided by my 3 expressed as a whole number, percent allowable, times my volts, divided by my nominal 120. Because table D3 is based on a 2-wire circuit, 1% voltage drop. That's where I generate my 3 from, because I'm allowed 3% voltage drop, not 1% voltage drop. 120 volt circuits, 2-wire circuits, plus the addition of the voltage of my calculation. So at that point in time, I'm looking at 90 meters divided by 3 expressed as a whole number representing the percentage times 120 divided by 120. 120 volts divided by my nominal 120. Realistically, 90 divided by 3, that's going to give me an approximate value, some sort of approximate value. Remember, I'm looking at 12 amps 90 meters away, so you can forget all of this if you want to do this calculation 5 times. You could start with 14 gauge conductors, you're not going to come close. You could do number 12, same multipliers. You're not going to come close. You can do it again for 10, not going to come close. Try again for 8, maybe 6, huh? Or just do this once. This will save you a lot of time on your CAQ. Guaranteed you're going to have a voltage drop calculation on your CAQ. So remember that part. For a 120 volt circuit and no more than 3% voltage drop. 3% multiplied by your nominal voltage, whether it's 120, 208, 240, 347, 600, whatever the case is, your nominal voltage is here. In this case, it's a 120 volt. 90 meters is my distance. Essentially, 90 divided by 3. I'm looking at a multiplier that I'm looking for 30 somewhere. This is the KISS method, the Keep It Simple Sean method, okay? So in table D3, when I'm looking at my maximum distance to my point of utilization for a branch circuit at 120 volts, trying to carry 12 amps 90 meters away, I go to table D3. Left-hand side, I scroll down in my current section, in my current column right here, until I see 12 amps. Well, I don't see 12 amps. I see 12 and a half. So I'm going to have to go by 12 and a half. 12 and a half. Now is when I use my approximate value. I'm looking for a number around the 30 area. It's a suggestion. Okay? But like I said, you could have tried that calculation at 12 and a half amps. You could have done for number 16. You could have done it for 14. You could have done it for 12, 10, 8. Oh, but man, look at that. 12 and a half amps. When we get a little closer to number 6, I got a multiplier of 31.4. That's good. I was looking for 30. Sorry, I was looking for 30 right there, but I see 31.4. That's nice. Let's try that. So I'm really concerned about my length, which is 90 meters, and I need to carry that 12 amps non-continuous 90 meters away at 120 volts with no more than a 3% voltage drop. So I realistically want the length of my conductor to end up being 90 meters or maybe more. Okay, so maybe pause right now and record that value. Okay, record that calculation to come up to our approximate. That 30 is an approximate. Okay, so maybe hit pause right now and record that value. 30 is the approximate that we're looking for. All right, so we were looking for 30 as a multiplier. I ended up coming up with a number 6 conductor that had a multiplication factor of 31.4 as a multiplier coming from table D3. Like I said, you don't have to memorize this calculation. It's literally in the code book. Okay, I'm just showing you how to run through it again because I'm not 100% sure that we actually did one in advanced. Okay, 31.4 is the multiplier for a number 6 conductor. Okay, at 90 degrees Celsius for a non-continuous load, my number 6 conductor should have an ampacity, okay, coming from table 2. I'm going to say it's probably around 65 amps. Okay, we'll double check that. We'll go back. Table 2. Ah, for Pete's sakes. 65 amps. We're just going to run with that number. Doesn't matter. You're going to make it. 31.4 is your multiplier. Multiply that by your nominal 3%. Double check. 65 amps Might be 75 amps. Let me be sure. Table 2, 9 degrees Celsius, number 6. 75 amps. That was right. I had a feeling about that. 75 amps. 75 amps. Good for a number 6, 9 degrees Celsius, 12 amps non-continuous. Okay, 75 amps. That 75 amps plays a factor in our distance correction factor. So I am looking at 3.14 times my nominal 3 as my allowable percentage voltage drop, multiplied by my volts, divided by 120. And then now I have to multiply that by my distance correction factor. Okay, so I'm using a number 6, 75 degrees Celsius, 75 amps ampacity on a 90 degrees Celsius copper conductor. Okay, I was looking for an approximate value around 30. That brought me to the number 6, good for 75 amps, coming from table 2. 31.4 is my multiplier that I generate from table D3. That 75 amps on that number 6 contributes to my distance correction factor as well as the 90 degrees Celsius rating on my conductor. So I now have to calculate my distance correction factor. At that point in time, you have to come up with two numbers. The first one, 90 degrees Celsius. The next one, a distance correction factor percentage consumption of your conductor. At that point in time, you're looking at a grand total of 12 amps on a conductor that's rated for 75 amps, which means you're using a percentage of that conductor. 12 amps total consumption on the conductor that's rated for 75 should get you a percentage value of that conductor. And if you go 12 divided by 75, you are using a grand total of 16% consumption of that number 6 copper conductor rated for 90 degrees Celsius. 16 whole percent. That's a good number for us to work with because I know that I can go pretty far now. I'm only using 16% consumption of the ampacity of that number 6 conductor. Okay? So I use those values, and I say that I'm using 16% consumption of that conductor, and now I want to take that value plus the 90 degrees Celsius rating of my conductor and go back to Appendix D to figure out what my distance correction factor multiplier would therefore be. Now I go back to Appendix D, Appendix B, go to Appendix D, Table D3, whoa, oh man, Appendix D, Table D3, and I take this 16% and that 90 degrees Celsius on installation rating of my conductors, and I go to Appendix D, Table D3 concluded. Take those two numbers, D3 concluded. I'll see in Table D3 concluded that I don't have a 16% column consumption of my available ampacity on my conductor. I don't have a 20, I don't have a 30, but I do have a 40. So 40 is going to be my smallest consumption of my conductor for my distance correction factor. And I'm also observing my 90 degrees Celsius rating. So I have to go to my 40% column and incorporate my 90 degrees Celsius to give me my distance correction factor. Now this is going to be a number around 1. And if you're only using 16% or realistically 40% consumption of your conductor at 90 degrees Celsius, you should see in that table that you come up to a distance correction factor of 1.08. That 1.08 is the code book saying, listen, hey, we recognize that you're using 40% consumption of your conductor. Okay, in this case, you're actually using less. You're using 16% consumption of your conductor. So we're going to give you a distance correction factor of 1.08, which means we're going to allow you to go 8% further on that conductor because we know you're not using very much. So I can get rid of this because you have that recorded already. And my distance correction factor now turns into 1.08. Okay, you have all that recorded. You're good to go for that stuff. Simple, easy peasy voltage drop calculation. Realistically, I'm looking to hit 90 meters. So I come up with 31.4, which is a number 6 conductor. Good for 75 amps. No more than a 3% voltage drop in that calculation. I'm looking at a nominal 120 volts for my circuit. And I've gone through and calculated my distance correction factor to be 1.08. So I can plug that calculation into my calculator. I can go 31.4 times 3 times bracket 120 divided by 120 bracket times 1.08. And I figure out that using a number 6 conductor good for 75 amps will allow me to run 101.736 meters in total. I can go 101.736 meters total using a number 6 copper conductor with 90 degrees Celsius insulation ratings at a non-continuous load of 12 amps with no more than a 3% voltage drop on a 120 volt circuit. Okay, that's the hard way of doing the calculation. The other way of doing the calculation is actually word for word in your textbook, in your code book, which you will have for your CAQ, and obviously you're going to have this for your final test. Okay, so I really hope that this video helps you guys out. All right, I wanted to make sure that this was recordable and you could go back over this again. Once again, record any of your issues, record anything that you want to talk about, any values, any calculations, and I'll see you on Friday. All right, this Friday coming up of your week 9, and I'll answer any questions that you might have. As always, at any point in time, you can always email me with any questions that you might have. I will get back to you as soon as possible. As soon as humanly possible, I will get back to you. All right. I will be on campus on Thursday. And other than that, I will see you on Friday. All right. I'll be on campus pretty much all day Thursday. If you want to come and see me, send me an email. I can go over this with you in person if you like. We'll find a spot to do it. All right. Other than that, send me an email. Let me know that you want to see me on Thursday. All of your pertaining quizzes are open on Fanshawe Online. I think you've been given multiple attempts to complete those before your final test. And then we'll talk again on Friday, and we'll do a test review. We'll schedule your test for next week. All right. Thanks, guys. I really appreciate your time. I hope you appreciate this video. It's taken me a considerable amount of time to create. However, I'm doing it for you because if I didn't have you, I don't have a job. So I appreciate it, guys. This is awesome. I really hope that you get some value out of this, and I pray that my audio is much better. I appreciate it, guys. Have an excellent afternoon. Take the rest of the evening off. Spend time with your families because I know you're going to be busy this week and next. All right. See you Friday.